and solving a mystery related to performance that we've kind of encountered. So the title is The Curious Case of Async versus Task, or alternate title, Mistakes Were Made. And we're going to discuss those mistakes as we go through it. They kind of get uncovered over time, a longer time period than I would have liked, but we're going to talk about that and what we learned from it. So this is me. I'm a big Pokemon fan. You're going to see that pretty fast. I have a Pikachu tattoo, but it's freezing cold, so you're not going to see that either. I'm on Twitter at Mr. J. Abbott, and I'm a senior software engineer for Incom Digital Solutions in Portland. We're hiring. We do F# all on the back end in some areas, not everywhere, unfortunately, but it's increasing all the time. And you can hit me up afterwards. So yeah, also shout out to our conference organizers. Thank them for making F# or OpenF# happen for the second time. This is a labor of love. So thank you, Matthias and Jen and Ricardo, wherever y'all are. Cool. So like I said, the scenario we're going to be discussing this is something real that happened. We basically were implementing service discovery, and so we wrote an adapter library for all of our microservices to use, with the idea being I need to get either another endpoint, whether it's like a messaging queue or a database or another server to request to. And so we wrote some abstractions around it to make that pretty common. It's not as sophisticated as some recent Jet blog posts about a similar problem that they solved, but the concept is the same. And so we decided on our own that we were going to write it in F# because why not? And but the key part of it is it also needs to be interoperable with all of our C# services in a way that's intuitive from a C# perspective. So we'll see what that looks like. So the requirements are pretty simple. We're abstracting a REST API, and we're going to expose a C# friendly interface. In this talk, we're going to use something else as an example. We're going to use Pokemon because, like I said, I'm a Pokemon fan. So we have a contract, and it's an interface, and we have one simple method that we're going to implement. It's called getCards. It takes a string and returns some data. It's going to return a task because we're going to be able, so we can wait on it. It also is returning a result on our C# microservices. We use something called C# functional extensions, which has a result type that's very similar to the F# result type, and you can interact with it in the same way, but it's very idiomatic for C#. For the demo, we're just using task because I didn't want to add another dependency in here and sort of distract from what the problem we're trying to solve. So the first thing we see is oh, I'm returning a task, and when you're dealing with this in F#, it's not super obvious how to do that. A lot of the documentation doesn't really talk about it, other than that obviously you can, because F# .NET and everything in .NET can usually talk to each other. So canonically, you would go Google, how do I weight a task, or how do I convert an async workflow to a task? So you read about them, and there's still not a lot of examples, or actually in the documentation there's really no examples. It does a great job of explaining asynchronous workflows and how they're different from tasks, but not how they should interact. So in an async scenario, or using an async workflow, I would use the async computation expression, which is exposed from the async builder. And in this scenario, we have some long-running task that's not that long-running or very realistic. And we return something. And then if I use it, I get back an async of some type. And until I actually explicitly execute it, it's just a specification of work to be done. In F#, the async workflow is subscribed to, it's called a generative pattern for asynchrony. Whereas the task-based model, you get a hot task. So when you get it back, it's already started. Whereas with an async workflow, it doesn't start until you tell it to. So cool, but that's not what I actually need for this library. So there's a couple of extensions I can use off of the async module or to do this. And so the first one being I can do async.start as task with my async foo, and now it's a task, and it's a hot task at this point. The hot task versus generative, async workflows isn't super relevant to the problem space we're in, but it's something to just be aware of. So how do I await something? There's this cool little helper method off of async called await task. So if I have something that's a task, I can await it in a way that's idiomatic for asynchronous workflows, do some extra work on it, and also here I can also return a task so that now I have sort of like the pieces I need to finish implementing my interface, or to actually start and finish it. So let's go do that. And if I go over to my library, so before we do that, let's look at the actual service that we're abstracting around. This is not what we're actually using in production, obviously, but too bad. This is a simple service. It's a .NET Core 2.1 Giraffe API. It has a single endpoint, and we're going to be abstracting it. It basically just has a single thing where you pass it a name and it returns some data. Not super complicated. And then in the library, I have some functions. The first one, and this is probably where like the first hurdle you would encounter if you were new to F# and you were trying to figure out how to interact with anything else in the .NET ecosystem, because everything else is task. It's like, well, how do I use this with my async workflow? And that's where our async await task comes from, and so I can get that response back and I could do something with it. This is not great production code because I really don't want to just get the message off an exception if it happens. I would like to know more about what happens. I probably want the stack trace. I might create some types around what these exceptions are. We're not talking about effective domain modeling or good application design. We're just talking about the meat of solving this problem. And then I have a couple functions here for deserializing and then doing some filtering to get the data I need out of it. These two are really, deserialization has to happen for me to do work on it. But some of these are here just to simulate some sort of CPU-based work versus IO-bound work, which is relevant to us talking about async and await and just asynchrony in general. And so then I can compose these together, and this will be the thing that we are going to be using ultimately. So absolutely. So I'll come back to the top. Thank you for asking. I have zoom it, and I can also do this maybe. Cool. Is that better? Sweet. Thank you for asking. So yeah, so this is the only thing that's really wrapped in an async right now. But this isn't something I'm going to expose to my callers because I have an interface to implement. So let's talk about that for a second. So we've seen the basic functions, we can compose them together so we can have the best of both worlds. I can write tests around the things that are pure, and then I can write some integration tests maybe for the thing that has a side effect, which is that HTTP call, but it's pretty simple. Those are the types of things where an integration test might not be super helpful because it's a known state, whereas when I'm actually deploying this, the state isn't necessarily known or as reliably. That's why you deploy early and often. We also want to be good stewards of our code and also play nice with our C# friends. So we're going to follow the F# component design guide. If you haven't looked at this before, I would highly recommend it. It gives you great guidance for writing F# libraries that are just for other F# applications. It also gives you some guidelines for writing F# libraries or applications that are going to interact with other parts of the .NET ecosystem. It's really well written. One of the key pieces in it that it talks about is favoring object programming, not object orientation. And this is true even if we're not doing C# interoperability, because sometimes I don't want to just pass around an HTTP client everywhere. That sounds exhausting. I'd like to have a single instance of it. You only want a single instance of it because otherwise other bad things will happen and you're going to be sad. But I don't want to have to initialize that somewhere, then pass it in every function, or partially apply it and get weird signatures and forget what my functions do. So I can create a class and put some methods on it that are basically just wrappers around the functions I wrote in a module somewhere. So this is how I would write a class and also implement an interface. So if this isn't syntax you're familiar with, I can do interface with the interface name and then with, and then the name of the method. And then inside of here I have another async workflow. And it's just calling that thing I composed. It's passing in that HTTP client that I don't want to pass everywhere else. I can encapsulate that in my object. And then I compose it together. And then at the end, I make it async start as task so that it actually matches the interface that we just saw earlier. And, happy sailing. So after we do that, we want to kind of wire it up so we can start doing some testing on it. And the testing that we're really worried about is testing at scale, whatever scale means for y'all. That's a term I don't really like, but it's people understand what that means. So scale for us, we're in the financial services kind of retail, like hybrid space. So for us, scale usually means Black Friday, Cyber Monday. Suddenly we're at like 5 times load or higher. We had some other things happen that will increase our load more than we expected in a good way, but we have to account for that also. So we also have to factor in like SLAs, like for certain customers, meaning like how long can a response possibly be before we've broken our SLA. So we're using ASP.NET Core. For this example, it's using .NET Core 2.0 because that's when we did this for real. This was a few months ago before 2.1 was official or was past like the release candidate stage. And so we go in here, and I have a controller. I wire up my adapter and my startup class. It's pretty simple. We're using dependency injection, which is a key tenet of most .NET Core applications. So I wire it up here inside of my container. It gets injected into my controller right here. I also have what's called a baseline service, and the reason this is here is so that I can benchmark against how this would be implemented like in a C# scenario. And so that way I can compare the results of the two and see if there's anything different or anything that I should be concerned about. I'd like to say we did this on the original scenario. We didn't. It turns out it doesn't matter. I'm not going to spoil any more. But I did it here for the sake of the example and to talk about like how we approach load testing and how to like create a baseline for the things we care about from a performance perspective. So I have a controller that has a route called async, and that's for the async call to our adapter. Async in this case doesn't mean async await. It means I'm testing the async workflow implementation that's wrapped with the async start as task and async await task. So here it is. Like I said, I didn't wrap like our C# functional extensions. This is the actual F# result. This would not be something that's in the component design guidelines, so don't do this. But like I said, I didn't want to add one more thing in here to distract from the problem we're solving. So cool. Here's my baseline service for comparison. It looks fairly similar. I have an HTTP client. I have a method. Again, don't do that. Down here, I do the same thing. It's more or less the same, except it's horribly verbose because C#. So sorry, C# friends. So we wired it up. So now we need to test it. And I can like do .NET publish and then .NET on the DLL to get like a realistic like scenario for it. I probably wouldn't do .NET run because that's not the same thing. So we set up our shared service, and then we set up the consuming service with the adapter. For this scenario, I'm putting them in containers where I can constrain the resources a little bit more. The reason I care about that constraint is that a 2018 MacBook Pro with 32 gigs of RAM may not be the same thing as a production web server. Different configurations, different operating systems, lots of things that aren't the same. It also makes it easier to run these tests. The test scenario is obviously we want to warm it up first so we can get like an idea of what it's going to be like when it's actually running. We don't want like the cold start to like influence our numbers, so we want to be aware of that. And then, so like I said, we set the baseline so that we can compare against the two and see if there's anything that's appreciably different about the two. This is a key part, number 3. The tests must be reproducible. So the tests I set up, I should be able to rerun these over and over again and see consistent results, or if they're not consistent, I need to explore why. And we're going to see what happens with that. So when we did our load tests in our real scenario, we used a tool called Vegeta. It's written in Go, cross-platform. We picked it because our previous load testing tools were JMeter, and I didn't want to install Java on anything because I didn't feel like do an Ask Jeeves load test. So we used Vegeta. That was recommended by somebody else on the team who was a big Go enthusiast, and I'm going to have words for him later, as you'll see why. So here's our test scenario. This is just a bash script. It has some arguments. The setup is Docker compose up in a detached state, so I don't have like the all the stuff writing out. And then I warm up my services. I'm passing in some commands to this executable with the attack argument. I give it a rate for the warm up and a duration. And then I just like throw away the result because I don't care. I'm just warming it up. And then I do it for real. And I have the rate as argument so that I can scale this up or down as I want. And then I write the results to some output so that I can run some reporting on it. Vegeta is really cool because it does have some interesting reporting stuff, and it's really easy to consume and read. So I really like it for that. And then I can go and run it down here. So this is all I had to do was say I'm doing some gets to these targets, which are the URLs. I gave it there's a name for it so that I can like have names to match to my results more easily. And then I give it some rates. And when we did this for real, we did several different rates. We did it at what normal scale is during a non-holiday season. We did it at projected scale for the holiday season. Then we did like higher than that because we want to be optimistic about where we're going. So we run those. Like I said, the test conditions when we did this for real, we used production-like servers, not the actual prod servers, because these weren't ready to go to prod yet. But we wanted to get a realistic idea from a hardware perspective, a network perspective, so on and so forth. The tests were run on the same box or the load tests, like executables on the same box because this is a service talking to another service on the box. We have this shared service for service discovery, and so the load needs to be on the same machine. Now, granted, we might be getting routed to another box, but this call is still coming from a local instance that's communicating this common state across all of our services. So this is some of the output you can get from Vegeta, and I'll zoom in on it. It's kind of cool. It gives you lots of really cool information. This was at 500 requests per second. So that becomes 90,000 requests over a period of whatever that math turned out to be, 3 minutes. And you can see some latencies here. 1.8 milliseconds. We can live with that. That's tolerable. And we get this cool histogram down here. And I can see that the majority of my requests were between 1 and 2 seconds, 92% roughly. And then they go down to like 2 to 4, and we get some like weird stragglers here. I would attribute those to probably some warming up changes or the thread pool like algorithm deciding I'm going to need more threads. So it wasn't ready yet for the load that it was about to receive. So then I get this cool histogram. And you can, this is really useful too. You can see most of our requests, like the meat of it is all under this 5 millisecond line. Some weird spikes in there, not super worried about those. There could be a few things that attribute to that. Maybe there was some GC happening, blah, blah, blah. Then we go up to 1,000, then we do the async version. That was the base, so we can say the base was whatever, 1.8. Then we do the async version, 2 milliseconds. So we're talking like 0.02 millisecond difference, not a big deal. The chart's a little bit different. Looks like there's more that fell into the 2 to 4 milliseconds scenario. That's kind of interesting. We're going to come back to that. That's the async plot. You'll see that there's some weird spikes at around 180 in the middle of it. We're going to come back to that. Run it up to 1,000 requests per second. There's not like some really appreciable changes. Actually, that's not true. We flipped from most things being under 1 to 2 to things being 2 to 4 at the baseline. Baseline plot's a little bit different now. We can still see the meat of it. You can see at the beginning, even though we've already warmed it up, that it's still having to catch up with the fact that it's getting hit harder. You can still see that it's mostly centered around like the lower end of the spectrum. We go to the async version. Our latency at the mean is 5 milliseconds, so that's interesting too. Maybe not as interesting. So it's 4.5 milliseconds versus 5. So again, not enough for me to worry yet. I get the report. The histogram is more or less the same. That's the plot. So this is what happened though, and this is on my samples right now. This is not the production stuff. This is the production test, or the production like server test. And these are supposedly warmed up machines. This was the async implementation load, and this graph is insane. And insane in a way that I'm a little worried about, like super worried about. And it's hard to explain what's happening when this happened. And it's been hard to figure out how to reproduce it since then. And that's where things get more curious than when I initially even proposed this talk. So we're going to learn a lot here. But this is really spiky and not something I want to see and have to worry about later. And all this red up here, these are actual errors where not sure what happened yet. I know now, didn't know then. But there's a few things, right? Like, first off, I'm running on Kestrel. If anybody's paid any attention to the Tech and Power benchmarks, Kestrel's a boss. Like, there's no reason for anything to not be awesome all the time. We're not doing anything super complicated here, so something weird's happening. Like I said, the test findings must be reproducible. At the time we were running these, we ran it multiple times, warm-ups, made sure that they were fresh DLLs. Everything was like following these processes, automated deployments, so there's not anything weird on the box, like it's the same process each time. We could reliably reproduce these results. I can't reproduce it now. Both scenarios were ASP.NET Core 2.0. I kept looking at the Tech and Power benchmarks for like JSON serialization and wondering what I was doing wrong. It had to be me. So between like the test for the sample and the test for there, the only difference is like this fake shared service. It's not nearly as optimized as the real one. We're going to see some results from discovery later that show that. But we also know Kestrel is super performant, and if we switch to 2.1, it's even more performant. So here's what we thought was happening, and this is not what happened. We're going to reiterate that later. We assumed that the conversion between an async to a task was where the majority of the problem was. There is a cost there. That's absolutely true. There's a cost of going back to an async. These are primarily IO-bound operations, which both async workflows and tasks or async await are great for. So there's not anything massive on the CPU side, so it's hard to understand what was happening. What we were interpreting from these results was that at scale, air quotes, asterisk, whatever, that because things were getting like stocking up, that there just wasn't enough bandwidth to finish the request. But that still didn't explain how we could look at these Tech and Power benchmarks and see something amazing versus this. It's very problematic. So how do we do that, or how do we resolve that? So even after, like, when we're going to discuss this some more, obviously, but there's a cost to those conversions. This is primarily IO-bound. Kestrel is super performant. Before we talk about some other stuff, we're going to finish the story with how we solved how we thought we solved the problem. Perception isn't the same as reality. The test did show us some gains, and before we go any further, I want to qualify this. I'm not somebody who's big on like micro optimizations. I'm not like a big fan of worrying about performance. That's really not my game. But we do have some requirements we have to meet from a performance perspective. We're going to try to figure out how to solve those. Development time is expensive. I'm not going to optimize for a problem we don't have, but we do have a problem. We do have a really great test-driven culture. That's why we have load tests and unit tests, and we write things in a way that they're testable. We have a realistic goal, and we want to test it based on our known business requirements, and then we optimize based on that information. This is one of those cases where we have a real optimization problem to deal with. And it's not as simple as, oh, we forgot to put an index on a database column. This is a real issue. How did we fix it? We found a task computation expression that's actually the same one Draft uses. We threw it in there. I don't have any more async await task or async starters task. This is purely on task now. And the only reason on my team I was one of the more experienced F# people. So I had remembered seeing this before. I've given talks about Draft and Saturn, so I knew this existed. I didn't add it immediately when we did this because I don't want to add dependencies we don't need. And so we added it, and we ran some reports. Now my latency for the 500 is more or less the same as it was in the baseline implementation. That's cool. The graph is pretty good. That's the plot, more or less the same. At 1,000 requests per second, the mean is 3.5. I can't remember what it was for the baseline, but they're pretty good, and we have a graph later that talks about that. Histogram is a lot better than what the async one was. And here's another plot. This plot's pretty consistent with actually the 500 requests per second, so I'm happy with that. The real results, I don't go up to like a second for some reason. And everything's more or less even. Now, this graph's a little bit different because it's an older version of the tool for load testing than the newer version. But the results look better. That's really cool. And here's a comparison of the data across all three of them. Here's my baseline, which is like the C# async await implementation compared to the task versus the async one. And the numbers are more or less the same. Now, this was weird between like the 3.5 and the 4.5. I think if I ran it a few more times, they would probably even out. But the graphs for these two and the numbers in general are really close together. And so we thought we solved it. And we actually did. That part's still true. But the problem isn't that we were using like async and task, or versus task. That turned out to be false. And so we're going to talk about now how I discovered the other part of this problem, which has nothing to do with .NET. As I started trying to increase load with Vegeta, I started getting really weird things happening. Requests were just being like canceled. At one point, I ramped this up as hard, or pretty hard, harder than I would normally throw at our servers because we would scale horizontally first. And my brand new laptop crashed, just completely crashed. Super cool. Tried a few things to fix it. Learned a few things around it. But we were seeing like the graph would suddenly be really, really red when we got to this high, and there was still not a good reason for it because, again, Kestrel, this isn't super complicated. And I looked at using something called Netlink for load testing because I don't want to spread fake news like we talked about this morning and say, always do this, don't do this. That's not true. So we used something called Netlink to do load tests again because I really was not sure what was happening, and I thought maybe there was a different problem. So this is Netlink. These aren't like all the tests I ran. This is more of the higher end load tests. I ran Netlink against the base. It has different arguments than Vegeta did. You can give it either just a count of requests to do, or you can give it a number of threads to use and a duration. I don't like the precision on that one, but it does some interesting things for us. When I said run it with, I forgot how many threads I said to use, but for 120 seconds, it was able to push through 182,000 requests on the base at 1,524 requests per second with 0 errors. And the median for it was 8.740 milliseconds. That's 500 more requests per second than we did with Vegeta. When I do with the async one, I get, as you can see, a few less requests overall, but the median time is still not bad, 0.1 millisecond higher. Go to the task version. I get more requests per overall than I did with async. It's pretty close to the base implementation. What I would expect. It shouldn't be as good because the C# compiler does some pretty sophisticated optimizations for async await that Task Builder can't do. It's a code-based implementation, not a compiler-based one. But they're still pretty close. There's some weirdness. Oh, it's not on that one. Okay, it's somewhere else. So we're good there. And then we get these medians, and we can start looking at them. And these are more in line with what I would expect. So I did this, and then I was like, well, I need to go rerun these against our actual production setup because this is really weird. And because I couldn't throw this at the production setup. It fell apart. It would have been an entirely red graph, no green. And we had some of those. And so I throw it at that machine, or I rerun the original tests. So I rerun them, and this is a huge number of requests, right, for 60 seconds. And look at my, and like I said, in the real world example, everything's a lot more optimized than what I'm doing in this example. This is crazy fast. This is not what we saw before. And I couldn't explain, I can explain it now. It's pretty crazy, and we're going to talk about it. But I'm still kind of like boggled by it. So this is with the, so this was the async implementation, 100, or whatever, how many that is, 1.2 million? Wow. No errors, by the way. This is after the warm-up, obviously. And then I do it for the task builder version. It's a little bit, you get a little bit more load, obviously. Median's 0.5. They're really close. Again, turns out that the async versus task part doesn't quite matter. It would if we had more task things happening, but in this scenario, it's not that. There's not a lot happening. Cool. So we go on, and there's some takeaways I want to talk about here. Originally, what I was going to say was we should pretty much, if we're worried about load, always use Task Builder. That's not true. I don't want to say that. Async is an awesome programming model. Async to task is also usually fine. If you are working with a lot of task-based APIs, though, I would strongly consider going down the Task Builder path, just so that you have a more consistent interface across them, and you don't have to worry about always doing like the await task and the start as task. You want to be you want to be a good partner to your C# libraries and the people like writing those or interacting with the ones that you wrote. Be mindful of your testing tools. So Vegeta is written in Go. Go's cross-platform, but as we all know, if you've done anything with .NET Core cross-platform, not all cross-platform stuff is created equal. It turns out what's happening on the Vegeta side is it's chewing up a ton of resources, and for each HTTP request it makes, that's counted as an open file. So you get to a point where, even though it's not really, it's not, but it is because operating system stuff, it's opening up files that are no longer then available for the application to respond to. So suddenly I get all these weird errors that I can't explain, but I can now. I'm very happy I can explain them now. That was very nerve-wracking when it happened. That doesn't happen with Netling. I don't know why. Netling is using the socket HTTP handler from .NET Core 2.1, so you can talk about maybe span, some other things in there. It's releasing resources way faster. That's probably a big part of it. And I have some resources here, but since I still have a little bit of time, I wanted to like dive into something I learned yesterday. If you guys are up for some live programming, that's probably a disaster. I think Sachi wants to see a disaster, besides the one from our load tests. So we're going to do some live coding real quick, and the problem I want to solve is I don't like, if I am going to do like async workflows, I don't want to have to keep writing the async.await task and async.startAs task. And so I can do something called a type extension on the async builder so that when I do a bind, it will convert that to a task behind the scenes, and the syntax is very similar. So we're going to do that together. It's one of those things where props to Ryan Riley for talking about it yesterday in our computation expression workshop. I've done lots of type extensions before, but I'd never thought about doing it on a computation expression because in my mind they're so different. Although the computation expression is based on a class, so just like any other class, you can like overload methods and so on and so forth. So I thought maybe we could all learn that together because it's probably valuable to be aware of. So I'm going to say open Microsoft. Oh, I got to spell it right. Live coding disaster. .control .async, or just control, I think. And then I can say type async builder with, or yeah, equals. Can't remember how to do it. We're going to cheat. HTTP or GitHub, right? GitHub.com/panes of glass. Repositories. There we go. Exercises. I need to remember how to do this. So this library is out there also, or this GitHub repo. It's really well written. So if you want to go learn how to do these later, there's a ton of really good examples. If you're not familiar with computation expressions or have never implemented them, there's some cool stuff in here on how to do this. I forgot how to do the type extension syntax though. Sweet. So I don't want to do this, but I do want this part because I can't remember how to do it otherwise. All right. So I want to say, when we do a let bang, that's actually a bind. So I'm going to overload the bind method. So this dot bind, and the syntax is flipped from when I write a bind, which means it's going to be, I always forget this one. So it's the member and then the function equals. I can do async dot, let's see, await task of m, or then I can pipe that to bind. No, I'm doing that wrong. So I can say async dot. I can say async builder dot bind. I could also do this dot bind if I wanted to. Bind. Or async dot bind. And so async takes in a binder, and it also takes in an async. So in this case, I can say async dot await task, and that's going to be my m, and I can pass that to f. Nope. Let's see. I'm going to look up my notes because I did this yesterday. All right, better. This dot bind. So this is my t, and that's my function. I can say this dot bind. Async dot await task of O, and then F. There we go. Or T, not O. And in this case, it's a task. So that covers the that task scenario. What if I want to do like the regular task, right? The one that doesn't have a type on it. I can do the same thing. I can give it a type alias though, or a type annotation, and say this is this task, not the other one. And it actually, oh, dang it. Yes, it is. Threading.tasks. Sweet. So now, if I do that, I shouldn't need this anymore. No red squigglies. So if I do have a library where I have to do this, this is all I have to do to solve that problem. And I think that's it. I don't have a good one for start as task. If I wanted to finish implementing this, I could, but I'm not going to. So trying to think if there's anything else I wanted to talk about with this. And that's it. So does anybody have any questions? Okay. Mm-hmm. I feel like the answer is, and I hate saying this, is it depends. I I would. Mm-hmm. I favor not. So the question is like, when would I use basically task builder versus async? Right. Mm-hmm. Right. Mm-hmm. It, I would say that it's not, so there's not a lot of scenarios where I would say like I would favor async over task. Right. I would say, so no, I wouldn't say there's a scenario where I'd go the opposite direction from favoring task, right? But I would favor not adopting dependencies I don't need. So if I am not doing a lot of like these conversions from task to async or vice versa, I'm not going to pull in a library to do that for me. Right. So things have changed a little bit too. Like there's not as many scenarios where they give you a synchronous option. So you will have more scenarios where it's always like the async, they're already the async like task version. But I've also noticed in .NET Core that a lot of methods that return tasks aren't even saying like async anymore because it's the only way you can go. There's an open issue on F# for adding a task computation expression as part of the language, and I think it's coming soon. And I think it's useful because when you're working with the rest of the ecosystem, nobody else uses like an async workflow the way they do tasks. Like I'm not going to go into my C# code and say and like do, async builder.bind to deal with an asynchronous workflow or something, and like async start. That's just not how that works. So I think it's useful for that perspective. But I would say, again, I think async workflows are perfectly fine, and as we've seen from some of these tests, they are close enough in performance that it doesn't normally matter. Right. Now, if you go back to component design guidelines, if I'm interrupting with a C# library, I need to do that in a way that is idiomatic for C#. So that's always the base for that. But if it's only being used for like F# stuff, I wouldn't worry about it. Are there any other questions? I wouldn't say about anything because I write stuff that sucks all the time. That's just part of it. There was some things that were unexpected in this scenario, and I think if I'm running tests against another server that I own, full disclosure, don't run load tests against somebody else's servers, please. That's not a good thing to do. If I'm running like Vegeta on one server against something on another server, I think that's a perfectly valid use case. It wasn't good for this use case because I was running them on the same server, which was valid for the scenario I was on. I would say in the future, I would probably just use the one now that I know what to expect from them. But they are, again, like you could use Netlink for both of those problems, but I liked Vegeta more from the data I got out of it. Like there were better presentations than what I got from Netlink, but which I think is key. But I did like I liked that I got the data that I actually cared about with Netlink. And not like a lot of this extraneous stuff that was not true and made me lose sleep. Kind of like prepping for this talk did. What other questions do y'all have? Dawn? I'm waiting to be crucified. Awesome. Well, thank you guys for your time.